Hello, hello, hello. This is Nicholas. In the last video, I talked about Clairaut's theorem. In this video, I want to use some of the concepts of partial derivatives in what we're going to be talking about is tangent planes instead of tangent lines, like in single variable calc. Tangent planes and therefore normal lines, because in order to define tangent plane, you need a vector normal to the plane. And then, as a result of this, also linear approximation. So the first thing that I would like to derive is the equation for a tangent plane. So remember that in single variable calc, we had a tangent line when we had a function of one independent variable. So we had functions of the form y equals f of x. Here in multivariable calc, we're going to have functions of the form z is equal to f of x comma y. And so this means we're going to be dealing in 3D, so the thing that will be tangent to our 3D surface will be a 2D plane. So I hope it's clear why we're using a plane here instead of a line. Of course, we could still have a line, but it sweeps through to create a plane, if you will. So let's say we have a function z equals f of x, y, and what we're going to do is we're going to parameterize it in terms of a new parameter, and I'll call it t because that's the usual parameter that we use. So we're going to have z of t being f of x of t comma y of t. And so then what we can do is we can use the multivariable chain rule. I haven't quite made a video on this, but the idea is pretty easy. So I'm just going to talk about it now. The idea is that we kind of have this, tree diagrams are often pretty helpful here. So we kind of have this chain of independence, or of dependence between the variables, right? So for example, we have f, which is a function of both x and y, but then x and y are both independently functions of t. So the idea is that if we were to differentiate this whole thing, we're going to get the derivative of z with respect to t, because we're differentiating with respect to our innermost independent variable, if you will. In other words, I want the bottom part of this tree diagram. So this is going to be equal to the partial derivative of f with respect to x times dx over dt. And so the idea here, where I get the, let me write the rest of it out, plus partial f with respect to y times dy over dt. So let me just say briefly where I get this. The idea is that in single variable calculus, you just had maybe a function f being a function of x, maybe x was a function of t, and maybe t was like a function of u or something. And so each time you went down this chain, it was another derivative, right? The idea here is that there's different paths we can go along this chain here because there's more than two dimensions that we're dealing with. So the idea is that, we start with f, and then we can either choose to go down x or we can choose to go along y. And so the idea is that whenever you're choosing a different branch to go off of, you make it a partial derivative, and you make it a partial derivative because it's only measuring change in one specific direction. In the case if you were to go along the x direction, you would have the partial of f with respect to x, or if you were to go along the y direction, you have the partial of f with respect to y. When you go along a branch that is one-to-one, in other words, you don't have a choice, you just go, if you're at x, you have to go to t, if you're at y, you have to go to t. And technically, you could write the partial of x with respect to t, but you really should write dx over dt. Technically, partial of x with respect to t is not wrong, but the partial derivative of x with respect to t is equal to the normal derivative of x with respect to t, since there's only one place that you can go from x to t, so there's only change in one direction to begin with. So writing dx over dt is simpler. Okay, after all that, hopefully what I have said here makes sense. So now, all I'm going to do is I'm just going to subtract this dz over dt. I'm going to get partial f with respect to x times dx over dt coming from that first branch of the tree, plus partial f with respect to y times dy over dt minus dz over dt is equal to 0. And we can actually think of this as two vectors, if you will. The idea is that we could split this into a dot product. So what we could do is we could call this, we could call the first vector partial f with respect to x, partial f with respect to y, and -1. And that's going to be dotted with dx over dt, dy over dt, dz over dt. And hopefully, oh, and this whole thing is going to be equal to 0 because it's equal to 0 up here. And hopefully you can see where I got that from. So I take partial f with respect to x times dx over dt, partial f with respect to y, dy over dt, and so on. And so we can split it up as a dot product like that. Now, just kind of converting to alternate notation here, that if I were to write this just kind of cleaner, that would mean we would have the vector f sub x, f sub y, comma -1, dotted with the vector x prime of t, comma y prime of t, comma z prime of t. Okay, so, oh, and that whole, let me move this over. Well, I'll just write it here. And that whole dot product right here, this whole dot product is equal to 0. So that implies then that this vector and this vector are perpendicular to one another. It should be obvious that this first vector, or well, I guess it's the second. The second vector here is just the tangent vector of our original vector function f of x, y. Because all we've done is we've just taken the derivative of each component, and the derivative gives us a vector tangent to the original one. Just definition of the derivative there. So now, if this vector is the tangent vector to the curve, then that means that this vector here, this f of f sub x, f sub y, comma -1, must be normal to the curve, and therefore defines a plane that is tangent to the curve. Because if you have a plane tangent to a curve, or a surface now, if you have a plane tangent to a surface, then you need a vector normal to the plane, and therefore normal to the surface, to define that tangent plane. So that means that this is our normal vector n. This is our normal vector n. And in all of these problems, we need a specific point to be given to us, because that's what it takes to define a plane as a point in a normal vector. So we're going to call our specific point x naught, comma y naught, comma z naught. So that means plugging into the equation for a plane, we get that f sub x evaluated at x naught, comma y naught. And by the way, normally they'll write it like this. Instead of x naught, comma y naught, comma z naught, they'll write x naught, comma y naught, comma f of x naught, comma y naught. Because once you have an x and a y, you can plug into your function f to get out that input z, which is f of x, y. So we have f sub x evaluated at x naught, comma y naught, times our x minus x naught, plus f sub y evaluated at x naught, comma y naught, times our y minus y naught, plugging into the planar equation here, plus z naught, which is f of x naught, comma y naught, and we'll write it like this. I want to be clean here. So this is plus, and now it's going to be a -1 because that's the z component of our vector. -1 times f of x naught. Okay, let me write it like this. Times z, I'll just write times z minus z naught for now. Times z minus z naught, couldn't decide. And that's all going to be equal to 0 because the dot product of a normal vector and any point on the tangent plane is 0 because they're perpendicular. And this is just the dot product. So now what we can do is we can simplify this just a tad. And I'm going to replace now z of z naught with f of x naught, comma y naught. And so I will get that z, our tangent plane, the equation of our tangent plane, is, and I'll just write f sub x, and we're just going to know it's evaluated at x naught comma y naught. So f sub x times x minus x naught plus f sub y times y minus y naught plus f of x naught comma y naught. And that's the equation of a tangent plane to a surface at the point x naught comma y naught. And notice that this is really defined much the same way, and it's very much a natural extension of a tangent line, because remember, our tangent line was, well, we had our y minus y naught is equal to m times x minus x naught, and then therefore y was m, which our slope, as we interpret it as the derivative of x with respect to time, or whatever you're using here as your independent variable, times x minus x naught plus our initial y naught. So this and this are very much the same thing. Here is like our change in the x part here, if you will, and then we add our change in the y part because we're in 3 dimensions, and then we have some initial point on the dependent axis. And so these are very much a natural extension of one another. So I think it would help to do an example of this. So let me find the numbers that I used. Okay, so let us do this here. So let's find the equation of a tangent plane to the surface f of xy equals x e to the xy. And that's going to be at the point 1 comma 0. I'll just leave it as 1 comma 0 for now. That's normally all they'll give you. And I'll just note that if they give you just the 1 comma 0, well, you plug in in this function here 1 and 0, and so you get 1 e to the 0, which is just 1. So our x, y, and z are 1, 0, and 1. Okay, so now what are we going to do here? Well, first we need to find our partial derivatives. So our partial derivative with respect to x is, and we're going to need to use the product rule here. So we're going to get e to the xy plus, we're going to get a xy e to the xy, and then we're going to evaluate this at the point 1 comma 0, and that's going to give us 1. Yeah, so now we find the partial with respect to y. That's going to just be x squared e to the xy, because this xy, x is a constant, so like 7y, for example, 7 becomes a coefficient by the chain rule, and so it's x in general. Now we're going to evaluate this at the point 1 comma 0, and we are again going to get 1. That's very nice. So the equation of our tangent plane, if I were to write this out in full detail, so it's f sub x evaluated at x naught comma y naught, which just turned out to be 1. So we have 1 times x minus our initial x point, which is 1, plus 0, our y, or we have our plus 1, our f sub y evaluated at x naught comma y naught, which also turned out to be 1, times y minus our initial point, which is 0, plus, now, this z part here is going to be, we're adding f of x naught comma y naught, which was 1. So that's just tacking on a 1 at the end. And so this is all equal to z, which means that if we were to simplify, we would get z being equal to, well, we have x minus 1 plus y plus 1. So this one and this one are going to cancel out. And we're just going to get our tangent plane is given by z is equal to x plus y as an example there. And so what does this mean as far as normal lines are concerned? Well, remember that if I were to just rewrite this a little, so I have x plus y minus z equals to 0, then the vector normal to that plane, and therefore normal to the surface, since the plane is tangent to the surface, is just given by the coefficients in front of the x, the y, and the z. So the vector normal to this plane is given by 1, 1, -1. And so if we were to take our point at 1, 0, and 1, and then just add or subtract some scalar multiple of this vector here, that would give us a normal line to the surface at that point. So in other words, our normal line, I'll just call it n, is given by, we would imagine, we would consider 1, 0, 1 to be like a vector, if you will, because we would then be able to add it with this vector. So we have 1, 0, 1 plus t. T is just some scalar multiple of our normal vector 1, 1, -1. And you could, if you wanted to be fancy, you could write this as 1 plus t, comma t, comma 1 minus t. And so this would give a line. It's technically a vector, but if you can kind of think of it as a line too, I guess. And that would be normal to your surface through that initial point x naught, y naught. And so therefore normal to the plane as well. I think with that,